Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. In the last 6 weeks of the course, we have introduced the basic material properties, and we talked about ideas of plasmon resonances and how electromagnetic waves behave in a periodic structure. And in the last week, we talked about metamaterials and metasurfaces. So in this week, I would like to touch upon an important class of materials which are known as tunable and active metamaterials or metasurfaces. The reason we are interested in these materials is that we have seen this structure, which is a negative index material, right? It works at RF frequencies. But so far from what we have seen, the resonance, the negative index is coming because of the overlap of the electric and magnetic resonances. And those are defined by structural parameters. For example, we have seen that the distance between the rings, right? The gap between the rings, and then the size of the gap, and then the whole area of the ring, and all that will determine your resonance frequency. So because these are reasonably large, these are fabricated on PCBs, you see that the resonance frequency is around gigahertz range. But if I make them smaller, then the resonance frequency increases. So this is something we have seen in the last week. Now, ideally for applications, we would like to have an ability to tune the resonance. It's not enough if you have negative index, let's say at one frequency, in this case 10.5 gigahertz, but we would like to maybe tune it to 10.1, to 10.5 and so on. So we would like to have post-fabrication tunability. Okay, so when you design, of course, you can design various structures with different dimensions and you will get different frequencies of operation. But can we tune it after the fabrication? Okay, so in the context of the negative index material shown here, this was the split ring resonator, right? And we saw that the resonance is because there is an L and a C in this structure, right? The inductance and the capacitance. And if you want to change the resonant frequency, you will have to change one of them. Okay. So one of the easiest things to change is the capacitance. So what we can do is, this is a schematic of, let's say, a split ring resonator. It doesn't really matter if it is circle or a square. It still exhibits the similar properties. And now we have seen that there is a capacitance in this part. There's a capacitance in the gap here, or also there's a capacitance between the rings. So when you have such regions, we can put a capacitor, external capacitor. Okay. In this case, one of the popular ways of introducing an external capacitor is a varactor diode. A varactor diode is simply a PN junction which is designed to operate in reverse bias, and it exhibits a large change in the capacitance with the applied voltage. Why would the capacitance of a PN junction change with the application of voltage? Well, there is this depletion region that is formed, right? And as you apply a reverse bias voltage, change it, the extent of the depletion region changes, and the space charge region changes. So essentially this device, a semiconductor diode in reverse bias, operates like a capacitor. Okay, and the capacitance is simply the epsilon of the material divided by the width of the depletion region. Okay, you would have studied that in semiconductor courses. So now I can connect a varactor diode across, let's say in this case, I'll drill a hole in the PCB, and then across 2 points I can connect them. Okay, this connection can be across this gap or this gap or this gap, depending on wherever we want. And various researchers have studied what is the optimal way. And we have also seen that the capacitance between the rings, right, is what is going to contribute significantly to our overall C. So it will be beneficial if you actually put it across this and then tune the diode capacitance. All right. So this is done experimentally in the RF frequencies. It's very easy to do because we have what is known as the surface mounted diodes, which can simply be soldered onto a PCB. Of course, it's tedious when you want to do it for each element, but then once you do it, you have a metamaterial, right? And that can be tuned. So this was done in the research community. And an example I'm showing in the bottom, wherein you see a notch filter. that was designed. So in this case, you have split ring resonators, and it's meant to act like a notch filter. Okay, so it filters certain frequencies. So what happens in this case is that you have this side, these are known as SMA connectors, and then you can connect a RF signal into that, and then you can transmit across this device, and then you will get the output on the other side using a vector network analyzer. If you do that, we'll see that it behaves like a notch filter, and the spectrum, the transmission spectrum S21 is a transmission spectrum, and you see that this it exhibits a dip at a certain frequency, that is a resonance frequency. So what I can do is I can apply an external voltage and change my capacitance. If I do that, I can see that my resonance frequency changes, and you see very nice variation of the resonance frequency here as a function of voltage. So 0 volts to 30 volts, as you change it, there is this variation, and that is causing the tunability of the notch filter. Okay, so we are seeing that from about 2.5 or so to about 3 gigahertz. So there's a large change of tunable response. Okay, and similar thing you can actually do for negative index and so on. All right. So tunable metamaterials are very important for practical applications, and this is one approach to do it in the RF frequencies. But if you want to do it at the visible or in the near frequencies, things get a little bit more challenging, because we have seen that in the RF frequency range, the metal is a perfect metal. Okay, the epsilon, you can think of it like infinity. It's very large. We don't have to worry too much about it. And then the design is easy, and the size of the structures are also reasonably large in the millimeter scale, which can be easily done by techniques like PCB fabrication. But the moment you want to do it at the higher frequencies, we have to think about different materials, and their response plays a critical role. In this case here, what I'm showing you is one of the approaches. So I'll just, in the next 10 minutes or so, I'll discuss a few tuning mechanisms that have been employed in the literature. The first one I want to talk about is the use of phase change materials. So what happens is, there are a class of materials which undergo a phase transition. We call it a phase transition. Essentially, think of it like, if you take a piece of let's say ice. Okay, it's in the solid form, it's in the and then if you heat it, it actually melts and it becomes a liquid. So it undergoes a phase transition from solid to liquid. Similarly, you can have a phase transition from, let's say, a crystalline form to an amorphous form. So in the schematic illustration here, this is a crystalline form wherein my atoms are arranged in a very nice periodic fashion, and if I, let's say, heat it, okay, then I can perhaps get into an amorphous form. So, and then back and forth. I mean, you can remove the heat, and then you can actually go back and forth between the crystalline and amorphous forms. The way these behave actually depends on material to material, but in essence, this sort of a material which exhibits a change in the phase, maybe in response to temperature, that's the most common lever. Those are called as phase change materials, and I'm listing a few examples of phase change materials. One of the popular ones nowadays is the GST. So it's a type of glass containing germanium, strontium, and I think that tellurium. I'm not sure. Yeah, it must be tellurium. And then vanadium dioxide, and then there are various other types of GST glasses. So there are a lot of these materials that are being explored, and they exhibit basically this property. For example, here, like if I take a vanadium dioxide sample, that has a critical temperature of about 70 degrees. So if I change my temperature below and above 70, the phase change occurs. When a phase change occurs, we have seen that the refractive index is very strongly dependent on the arrangement of atoms, right? So we should expect a change in the refractive index, and that is what is shown here. So at a wavelength of visible 630 nanometers and at 1500 nanometers, you see that the first column, the first number here is the minimum refractive index. So let's say for vanadium dioxide it is 2.56, and then followed by we have a delta n, which is a change in the refractive index from amorphous to crystalline form, and you see that there is a 0.1 refractive index change, and the k value also is given to us. So basically what we see is there is a change, and the visible range, it doesn't change so much, but in IR you see that immediately there is a 1.4 refractive index change. So that's a significant amount of change in the refractive index. And if you go to mid IR or or terahertz range, you'll see much more stronger change. And one experiment with phase change material, wherein a split ring resonator is coated with a phase change material and it is heated. In this case, the heating is done through applying a current source across the material. So when the current passes, it heats up the structure and it causes a phase transition in the vanadium dioxide, and because of which the resonance is shifted. So this is a example taken from this paper here from Driscoll. It is published in 2009. So you see that we can actually change the resonance properties. Okay, and there are various other materials. One key point I want you to look at is the extent of change and the switching speed. Okay, so if I look at all these materials, let me identify, let's say here, this GSST has a large change, 1.9 change in the refractive index. Similarly, let's say antimony selenide has 1.17. So these have very large change in the refractive index, and that's something very useful for us, because the moment the refractive index in the surrounding environment changes, the resonance property shifts, right? We understand that already. And if we see a large change, it turns out that the speed with which you can actually change it is not very high. So in this case, it takes about 100 milliseconds, and this is again similar 100 milliseconds. So what you see is whenever you have a large change in the refractive index, the switching speed tends to be small. Okay, or sometimes you might even manage to get a large, reasonable switching speed. Like if I look at this particular case, I have 0.89. Switching speed also seems to be reasonable, but then we also have to think about the energy and the temperature at which the phase transition happens. So in actual devices, the amount of flexibility that we have, I mean, the performance is going to depend on various metrics, and I would say that scientists are still trying to understand these materials and use them. So I would say that at this point there is still no clear cut material of choice. For example, electronics, everybody uses silicon. There's no other option. I mean, there is no other material that is seriously considered. I mean, nowadays we have other materials, but still electronics is by far the most popular semiconductor, right? I mean, compared to germanium and gallium arsenide, and there are reasons for that. But you don't see such a trend in these cases. We have various materials that people are still growing and depositing, and then trying to study their properties and trying to achieve large tunability. Okay, this I would even call it electrothermal. So because in this case, in this example here, you're passing a current and heating it, so electrothermal, and we want to do it at a low enough temperature. We don't want to increase the temperature to, let's say, 280 degrees, which becomes difficult to, because you can have melting of these nanostructures at high temperature. So there are various constraints people are still looking at. So it's an active area of research. So this is the first type of tuning mechanism I wanted to talk about. In addition, we also see that there are other mechanisms. For example, we can use what are known as liquid crystals. Liquid crystals are again another unique material. So what happens in liquid crystals is they are actually they are like liquids. They can flow like a liquid, but if you look at they consist of molecules which can be oriented, like what you see in crystals. So we call them liquid crystals, and they're already very popular. I mean, it's been a very well developed technology for a long time, because calculators, we have LCD displays, right? So those are all liquid crystal displays. LCD is liquid crystal display. Okay. So what happens in this case is you can have these elongated structures represent the crystal, liquid crystal, in the individual molecules in a liquid crystal, and when we apply an electric field, they tend to get oriented. Of course, these properties depend on the type of liquid crystal. There are various liquid crystals that are available in the community. They're well developed. So you see that the orientation of the liquid crystals is fixed. When you don't apply any voltage, this figure is slightly misleading, but in general they tend to be randomly oriented, and they get isotropic. So this is misleading. I'll just simply say that you can have a isotropic phase, and that can to oriented liquid crystals. Okay, this is called as a nematic phase in the community. Nematic liquid crystals, NLCs they call them. All right. So by applying an electric voltage, I can actually change my orientations. That's one possibility. Okay. When you do that, these crystals actually, because of the orientation, the refractive index changes, and we can observe this. So this is an example. I'm just showing an example of a liquid crystal. This was the the magnetic strips that we talked about, and when we talked about the magnetism in the visible frequencies. So you have these magnetic strips, and if you cover them with a liquid crystal, this 5Cb is a type of a liquid crystal, and then heat it, and we can observe the response. So the experimental data is shown here. So you have without liquid crystal, there is a curve, and then there is simulation and experiment as well. So basically you see that the moment I apply a liquid crystal, the resonance shifts because the surrounding environment has changed. And then by changing my temperature, going from 20 degrees to 50 degrees here, I think the liquid crystals transition, from isotropic to, I talked about the electric field causing the orientation. Even the temperature can actually cause that. If you increase the temperature, it would change. And you see that with different temperatures, you see the resonance is shifting. And this is again one example of how liquid crystals can be used for tuning resonance. Okay. There are a number of papers in this direction, but I must point out that liquid crystals in general take longer time to respond. Okay, so in the previous case, we have seen that the energy and the speed, right? The speeds are in a range of nanoseconds, but liquid crystals will take milliseconds or even more, tens and hundreds of milliseconds. So it takes long time for them to respond. They're not very fast because again, this is orientation of the atoms or molecules, so it's in general a time-consuming process. All right. So this is the second tuning mechanism that I wanted to show you. And the third one is a very simple idea that, some people have tried. I would say that it can actually give you a large change, but it's not, it's cumbersome. Okay. We have to have a very robust material. So the idea is that, let's say we'll take the split ring resonators and we fabricate them on an elastomeric substrate. Now, for example, PDMS is a very popular one. PDMS is an elastic sort of a polymer which becomes like you stretch it, like like you stretch a piece of rubber, right? When you stretch it again, you can actually push it, leave it. When you relax it, it comes back to the original dimensions. So if you fabricate the metamaterial in this case on top of a stretchable substrate and stretch it, you see that there is the gap between the elements in a split ring resonator changes, and that gives you change in the resonance frequency. It's a very simple idea. So on the right here, you see the SEM images of, let's say, initial unstretched, resonator, double split ring resonator, and then as you change the stretching, you stretch it by 10%, 40%, and so on, you see the dimensions change and the gaps change. And eventually, if you leave it, it will come back. You see already that, if you relax back, it's still not looking the same as this. Well, I would not read too much into the images here because the imaging was done on PDMS, which is a charging substrate, and it becomes difficult to look at it. All right. So, but you see the overall idea that as you change the percentage of stretching, the resonance position also changes. So you see, originally you have here the resonance. This is the reflection. Reflection peak denotes a resonance. So whenever a resonance occurs, you see a peak in the reflection, a dip in the transmission, and a peak in the absorption. All right. So you see the position of the peak is changing. And then when I relax it, okay, it looks like it's coming back to where you are, but there's a slight shift. All right. So this is how the switching in the you can tune, but it becomes slightly harder to implement this. I'll show you one more example of this slightly later. All right. So you might even wonder, what is this notch here? This looks like a very strong thing. This is basically, I think, water absorption. This measurement was done at, this peak occurs at around 3.3, 3.4 microns. It turns out that these are, IR ranges, and you measure this with what is known as FTIR. And then there's a lot of water peak that can, that is water absorption happens, and because of that you see a very sharp dip at that. So this is a standard thing. All right. So we can ignore this safely for our purposes. So this peak is, the overall peak is this. That is the resonance we are talking about. The sharp peak we can ignore for the moment. All right. So this is the third mechanism that I want to show you. And then there is again, fourth mechanism, which I'll call as carrier injection. The carrier injection can happen by multiple techniques. I can shine an optical pulse, which causes the carriers to be introduced. We can excite electrons and electron-hole pairs. For example, in a semiconductor, that's what is shown here. We'll take a gallium arsenide nano antenna sandwiched between two structures, and then we pump it with, let's say, a pulse, and then we introduce lots of carriers, and that carrier changes refractive. That causes additional carriers cause the refractive index to change. So in this case, these are me resonances we talked about. So the mode that is excited in this is very sensitive to the carriers. Okay. So because of that, we can tune these things. And the important fact here is that this, when you shine light, you're creating electron-hole pairs. So this is a non-equilibrium situation. And so after some time, let's say in the range of few tens of hundreds of picoseconds, the carriers will relax back and this effect will vanish. But in that short time frame, we can introduce a change in the resonance. All right. And we also will have we can also introduce by electrical means. So I apply, I have a, I can think this is, I think, a gallium arsenide substrate with a metamaterial on top. And if you have a Schottky contact, and then as you change the voltage, you will actually introduce carriers into the structure, and then that will cause a tunable response. This is one of the famous initial papers. I think it came out in 2000s. Well, 2006. All right. And then and you can also inject, again, the similar approach. We can introduce nonlinearities in this by using a strong pump, and that will also cause change in the optical, the transmission. Okay. So various examples I'm showing you by carrier injection. All right. So you might say, okay, yeah, there are these various approaches to tune, but what has been really achieved? Okay. So I just picked up a couple of examples from recent literature. So this is one idea where they fabricated a sort of a beam which is used to focus light. Okay. And then as you stretch this metasurface, you will see that the focal length changes. So you would like to have variable focus lenses. Lenses usually are fixed, unless you have a big mechanical adjustment mechanism. Like in a binoculars, you move it, and then that causes the distance to change between the lenses, and you can change the focus. But that's bulky. How do I do that in the on the chip, or in a micron scale? So one of the ways could be to use some sort of stretching mechanism like this. So you see that as I initially have the focus, which is at some distance of 150 microns, and as I stretch, the focus is shifting to 200 and 250 microns. So this is basically, you can think of it like the focusing of the optical beam. So I have, if this is the axis in which the light is propagating. So at this position, away from the lens, at around 150 microns, you see the focusing of light, and as you stretch it, the focus spot is shifting to 200 microns and 250 microns. So we're able to change the focus with stretching. That's one example. And the other example I wanted to mention is this is still, I would say, active area of research, wherein we have this kind of grating structures, and they are fabricated on top of what is known as ITO. This is a indium tin oxide. It's a semiconductor. Well, it can actually be, you can introduce carriers into that by electrical voltage, and then you can create these charges, and the charges will cause the response of this grating to change. And so people are looking at these things for what are known as spatial light modulators. So can we make a compact spatial light modulator that can have a lot of applications in things like LiDAR and so on. So I think this is a work from Samsung. Samsung is actively looking at this, and they're trying to have let's say an incident beam like this, and I'll control my direction in which my reflected beam goes. I want to steer this beam. That can have a lot of interesting applications in things like augmented reality, or head-mounted displays and so on. So the structure internally here is that you have this substrate, and then there is an insulator, ITO, insulator in metal. So when I apply a voltage here, just like what happens in a MOSFET, I'll see the carriers which are accumulating under the metal, and that will cause the change in the change in the material response. So these are some examples of applications that are being pursued in recent times. So there are a lot more things people are looking at. So before I close my discussion on the tunable metasurfaces part, I just wanted to bring to your attention the performance metrics. So when we think of tunability, when you open any research paper, there are lots of research papers if you look on Google, but each of them addresses some part of the problem. So we are still looking at a comprehensive solution. So what are the various performance metrics that we like in a tunable metasurface? So the first one, of course, we should have strong modulation. Okay, modulation depth. By which I mean, for example, if I have a metasurface which has a reflection peak, so I would like to know what is delta R, reflection divided by R. So I want a strong change in the reflection, or maybe strong change in the transmission. So these are some parameters that I look for. Okay, so modulation depth, how strong is that? And the second thing I'm interested in is modulation speed. Of course, I want it to be as fast as possible. Okay, and the third one I want is what is the energy consumed, right? Energy consumed. I don't want to spend a lot of energy just to create. So I don't want to spend a lot of energy. So that is an important one. We mentioned in the initial slide on the phase change materials, there's some femtojoules per nanometers cube, right, or nanometer square. How much energy is required to cause the phase transition? We don't want to spend a lot of energy. And the fourth one, of course, also is the wavelength of operation. We'll see that it's not easy to change refractive index or the optical constants at small wavelengths. Visible it becomes difficult, but in IR and terahertz it's much more easier to change the refractive index. All right. So there are in addition there can be other metrics as well. So if you look at the research in the last 20 years, you will see that there's a broad range of things that are explored. I just gave you a glimpse of some of them, like phase change materials and electrical injection. There are also 2D materials, graphene. I had worked on graphene for some time. So graphene is a very interesting 2D material that exhibits a strong change in the IR. So the various ferroelectrics and so on, there are various materials. And if you look at them broadly, this is a very nice research paper that just came out, and they're talking about the modulation speeds, very high speed, and also the depth. So ideally we would want to be here, high speed and strong modulation. And again, so in this case it looks like some of the materials that are very useful are phase change materials. And of course, if it is phase change materials, again each of them differ in how the modulation happens. If you design carefully a structure, we could in principle have a very strong modulation depth at high frequencies. And if you come down to other types of material like liquid crystals and so on, they have very, very small modulation speeds, so kilohertz speeds. And it depends on the configuration where they're trying to show. You can also have large modulation depth with liquid crystals. Even though I'm not sure which example was this, there should be other liquid crystals which are actually having much higher modulation depth and lower frequency. Okay, we'll have to go and look at the literature where exactly these things are done. So this paper gives a very nice review of all this. And when you have electrothermal, means you pass current and then heat it. So that is usually slower. Optical thermal, that means I shine a high energy pulse and then heat it. The response times in this case is 10 to hundreds of picoseconds, whereas electrically it takes much longer to actually heat it. It's an I²R heating mechanism, so it's much slower. And so you have various things that are there. So if you're working on this area, I would urge you to look at various metrics that I listed here. So ideally we would want a tuning mechanism that satisfies all of them. So how do we achieve that is an open question, I would say. But it looks like, liquid crystals are not really that easy to manage because of other issues like, they tend to aggregate near the surfaces and so on. They're not that easy. Phase change materials are good, and semiconductors are also good if you can modulate them. The semiconductors also have this additional advantage of being compatible with existing fabrication technology. So that they're useful for that. And we can have carrier injection that is very well understood, or carrier movement which is very well understood in semiconductors. So so this is what I wanted to tell you about tunable metasurfaces. So I'll stop here for now, and then I'll continue in the next lecture wherein we'll discuss other aspects of active metamaterials. So I'll start with a discussion about optical gain, and then how optical gain can be used. So far we have looked at passive structures. That means they're not really generating light. We will talk about light generating structures. All right, this is the focus of the rest of the week. So thank you very much for your attention. I'll see you in the next lecture. Bye.